This is section 14.4. We're going to be talking about flaws of apportionment methods. First one we're going to talk about is called the Alabama paradox. When you have an increase in the total number of items to be apportioned, this results in a loss of an item for a group, you have what we call the Alabama paradox. So here's an example. We have a small country with a population of 10,000, has 3 states, A, B, and C. According to the Constitution, we have 200 seats in Congress. So here's the state's populations, and we have 200 seats. So what we're going to do is figure out where those 200 seats are going to go, how they're going to be distributed. So as you recall, you're going to need the standard divisor, which is the 10,000 divided by the 200. So we take the 10,000, which is the total population, and divide it by the 200, and that will give us a standard divisor of 50. What we're going to do is use Hamilton's method and show that the paradox occurs if the number of seats is increased to 201. So to do this, you're going to use Hamilton's method twice. You need to do Hamilton's method with the original seats of 200, and then you're going to do it with the increased seats of 201. So we got the standard divisor. We're going to divide each of the populations by the standard divisor, and that will give us the standard quota. So the standard quota for state A would be 100.3, B 90.3, C 9.4. Hamilton's method, if you recall, means round down. So 100.3 rounded down will give you 100, and 90 and 9. If you add those up, it adds up to 199, which gives us 1 extra seat that has to be given to somebody. With Hamilton's method, you give the extra to the highest decimal part. So the highest decimal part is state C, which is 0.4. They get the extra seat. So the final apportionment, 100 seats for A, 90 for B, and 10 for C. That's with 200 seats. We're going to repeat the process with 201 seats. So we need the new standard divisor, total population, divided by the 201 seats will give us a standard divisor of 49.75. Repeat the process, divide the population by 49.75, and find the lower quota. So 10, 90, and 9, that hasn't changed. But now let's take a look at the decimal part. The decimal part now is 0.80, 0.75, and 0.45. Now state A has the largest decimal part. So we're going to give the extra seat to state A, but notice this adds up to 199, and we have 201 seats. So we actually have 2 extra seats. So we'll give 1 to A, and we're going to give 1 extra to B. Well, originally, we gave the extra seat to state C. Well, we didn't give an extra to state C this time, so their number of congressmen went down from 10 to 9. Even though there's 1 extra seat in Congress, they lost a seat in Congress. So that's bad. That's called the Alabama paradox. For any of these paradoxes, if the apportionment goes down, that's a warning signal. It's not always a bad thing, but usually that's a good indicator that you're going to have a paradox. The population paradox, Group A loses items to Group B, even though the population of Group A grew at a faster rate than that of Group B. All right, so again, we have the 10,000. For the population, we've got 11 seats in Congress. So here we have the original, and here we have the increase in population. So state A went from 540 to 560. The total went from 10,000 to 11,000. What we need to do is figure out the percent increase. To figure out the percent increase, you subtract the two numbers and divide by the original. Percent increase. Subtract the two numbers, divide by the original. So the percent increase for state A, 560 minus 540, subtract the two numbers, divide by the original 540. So 20 divided by 540, make it a percent, we're talking about percent increase, a 3.7% increase. Do the same for state B and state C, 4.9 and 12.2. Now what we want here is to look at who has the largest percent increase, who has the next largest percent increase, etc. You notice state C has the largest percent increase, then state B, and then state A. Okay, so you're going to have to keep that in your head. You need to know those percent increases. Again, we're going to use Hamilton's method. You're going to use it for the initial population. You're going to do it for the new population. So total population, number of allocated items, standard divisor of 1,000. And the final apportionment right here. State A has 1, State B has 2, and State C has 8. This is the new apportionment with the population of 11,000. Under the original apportionment, which I did not show you in the notes, State A originally had 0 seats in Congress, but now they have 1 seat in Congress. State B had 3, now they're down to 2. Notice this guy went down. That's always something to watch out for when we're talking about paradoxes. And C stayed the same. Alright, so take a look here. Now, if State B had a smaller percent increase than State A, because this guy stayed the same, so that doesn't count. We're not worried about C. If B had a smaller percent increase, then it's okay to lose a seat in Congress. But if you take a look at the percent increase, State B actually had the larger percent increase, so they should not, larger than State A I'm talking about, so they should not have lost a seat where A gained a seat. Population paradox. New states paradox. The addition of a new group changes the apportionments of other groups. We've got 2 high schools, East High and West High. The school district has counseling staff of 48. So that means for every 200 students, you need to hire a counselor. Standard divisor is 200. Hamilton's method again. Final apportionment, we have 8 counselors for East High and 40 counselors for West High. We build a new high school. We've got North High. And now North High adds 1,400 more students. So since we need a new counselor, or we need a counselor for every 200 students, that means we need to hire 7 counselors. So the school district does. We now have 7 more counselors. So instead of 48 counselors, we now have 55 counselors because we added 7 counselors. And instead of an original population of 9,600, we got a population of 11,048. So the new standard divisor is 200.87. Hamilton's method, we get a final apportionment of 9, 39, and 7. Now notice, originally East High had 8 counselors. The 7 new counselors go to the North High School, which is as you would expect. But West High went from 40 counselors down to 39. So if everything were to be fair, that wouldn't have happened. If everything had been fair, East would have kept 8, West would have kept 40, and North would have gotten the 7 new hires. But instead, West decreasing congressmen or counselors, and therefore we have a paradox. Belinsky and Young's impossibility theorem. What this says is that there's no perfect apportionment method. It's not possible to apportion perfectly. Any apportionment method that does not violate the quota rule must produce paradoxes, and any apportionment method that does not produce paradoxes must violate the quota rule. So in other words, it's impossible to apportion items in a fair manner, fair to all. Homework is 2 through 12 even.